All right. So, good morning. Welcome back from your quiz. Hopefully, people are back. I mean, give folks a minute or two to roll in. Um, you guys all know who I am. I don't think there's anybody out there who doesn't know, but for those who don't, just in case anyone watching, my name is Bruce Armbrust. I'm another one of the math faculty, and I'm just filling in for Larry today because he's got another meeting that he needs to be part of. So, I'm going to do my best to fill his shoes. And today we're going to talk about a couple more tests called the ratio test and the root test that we use to check convergence and divergence of infinite series. But before we get that, Larry asked me to go ahead and go over the quiz with you guys. So let's go ahead and start there. I'm going to share my screen. Hopefully he's got it enabled that anyone can share. Looks like it. So I'm going to pull up a whiteboard here. So for your quiz, the first question was asking you just to determine whether these series converge absolutely, conditionally, or diverge. And so the first one was the sum from -1 to the n plus 1 over 4 to the n. All right, I don't remember where the starting number is, but hopefully you guys understand that where it starts doesn't really matter. All that really matters is that we go to infinity, because when we talk about convergence or divergence, it's always what's happening at the very end, right? The first, first finite number terms, you don't care at all. So anyway, um, so I know you guys just did this one. What did you guys find? Did this converge absolutely, conditionally, or diverge? Go ahead and throw it in the chat or yell it out. All right, so Susanna says that it converges. Thanks for offering that up, but I'm actually going to ask you a follow-up. Converges absolutely or conditionally? All right, so Adam just said absolutely. Yeah, and this one does converge absolutely. And let's actually show why that is. So for conditional convergence or absolute convergence says that the sum of the absolute values of these terms converges. So let's look at this sum. The absolute values, that's just going to make it so that it doesn't alternate anymore. So this is the same as 1 over 4 to the n. And we know that this converges because hopefully you can recognize that this is geometric. And it's geometric with r equals 1/4. So the form, what tells me this is the fact that it's raised to the n power. When you have something raised to the n power, it's going to be geometric. When in doubt, this is some advice I always give students. When in doubt, if you're like, man, I don't know, I can't tell, write out the first couple of terms. I'm going to go with that this thing started at 1. But that would give you 1/4 plus 1/16 plus 1/64 plus. And sometimes when you write that out, it's a little bit clearer to see the patterns. And you can recognize, oh, I'm multiplying by 1/4 every time. And so since that r is between plus and minus 1, that's what tells me that it converges. So since the absolute values converge, then the series itself converges absolutely. All right, so there's number 1, or I guess 1A. 1B, this is another alternating series. Looks like that. So let's actually do the same test because we want to see if it converges absolutely. So this is going to be the sum of 1 over n minus 1/2. So what can you tell me about this series right here? Not the original series, but the one of its absolute values. Okay, so Alexi just said that this guy diverges, and it does, absolutely. It diverges, and technically what you would probably do is the limit comparison test with 1 over n. We know the harmonic series diverges, and if you do the limit of the ratio of these two terms, you get 1, which is a finite positive number. You could, so direct comparison test, Alexi, the reason I avoid that is because suppose, well, think about the difference of 1 over n minus a half and 1 over n plus 1/2. One of those is going to be bigger than 1 over n, and one of those is going to be less than 1 over n. And the direct comparison test only is going to apply to one of them, but the limit comparison test will actually take care of both of them. So can you use the direct comparison test? Well, let's just see. Are these terms bigger than 1 over n? Well, yeah, they are, right? You plug in 1, you get 2 instead of 1. You plug in 2, you get 2/3, which is bigger than a half, and so on. So this one, also the direct comparison test would work. But notice that that required some thought. And you guys know me. You know how I'm all about being lazy, because I'm convinced a good mathematician is lazy. So I find that the limit comparison test is much better, especially when you're dealing with things that are ratios of polynomials, right? When you're dealing with rational function. So I would do limit comparison test, but in this case, direct comparison test works as well. All right, so the absolute value of this series diverges. So now the question is, what about the series itself? Well, the series itself is going to converge. Why? What test tells me that this converges? Yeah, we're going to use the alternating series test. Thanks, Susanna. This one, it's going to be the alternating series test. The -1 to the n tells me it's alternating, so I like that. And then for the alternating series test, remember what you need is the underlying piece, the 1 over, in this case, 1 over n minus 1/2. That has to go to 0. And that definitely does go to 0 as n gets bigger. So the series itself converges, but since the absolute value of the series does not, we're going to say that this converges, oops, that's about right, converges, diverges. Converges divergently? No. Converges conditionally. And you'll have to forgive me. I haven't had to teach this early in the morning for quite some time, since I was with you guys in March. So, all right, so that one converges conditionally. So then if we go to the third one is another alternating series. So we have -1 to the n times n minus 1 over n plus 3. All right, so what about that one? What does this one do? All right, so it definitely diverges. Thanks for that, Susanna. So this guy diverges, and I'm going to guess DT probably means what? Divergence test?
Yes.
Yep, okay, cool. I call it the test for divergence, but I figured that was the same. Yeah, if you look at the underlying piece here, the limit is n goes to infinity of the -1 to the n minus 1 over n plus 3. This does not equal 0. In fact, this limit doesn't exist because you're going to bounce around between numbers that are getting closer and closer to +1 and -1. And we know that in order for a series to converge, those terms have to go to 0. All right, so for those 3 series, it's converges absolutely, converges conditionally, and then diverges. All right, so then that leaves us question number 2, and I got enough space over here on the side. We'll go ahead and do it over here. So for number 2, we have another series. This one I did keep track of what we're doing. We're going from 1 to 5, -1 to the n over n cubed. And the question is, how good of an approximation is this? to the infinite series value of -1 to the n over n cubed. All right, so the maximum error, how do you figure out your error, or the absolute value of your error for one of these? Okay, so Susanna just put in there, so it's the absolute value of s minus Sn, and that's true, like that is what our error is, but we don't know what S is. But then Adam and Alexi just sit there, plug in n plus 1. Yeah, you just go to the next term. You go to whatever the next term is, and that is that is worst case scenario, you're off by that much. You're actually going to be off by less, but that's the best we can say at this point. So what we really need to do is look at the sixth term. So if we look at a sub 6, we get the -1 to the 6 doesn't really matter, but we'll go ahead and put it in there to get our a sub 6. And so this is 1 over 216. We're looking at the absolute value of the error. So whether we're off by, if we're over by 1/216 or under by 1/216 doesn't really matter. But for sure, we know we are within 1 over 216. Okay, so our error is going to be less than that. So think about this. That's already a pretty good approximation. 1 over 216, that's 0.005, roughly. So whatever decimal value we would get for the sum of the first 5 terms here, we're within 0.005 of the actual value of that sum. Depending upon how good of an approximation we need, you can see how fast this is, right? You can get really good values without a lot of term. All right, so cool for that one. All right. Okay, so there was your quiz. Hopefully it went well for you. If not, at least hopefully you can see kind of the approach to take. All right, so before I dive into ratio and root tests, are there any other questions over homework? We can spend a few minutes looking at some problems if you would like. All right, I'm not seeing anything, I'm not hearing anything. So I'm going to take that as things are going pretty well and we're ready to kind of move on. All right, so I'm going to go ahead and hop up to my whiteboard. You may have seen I've got a second screen. For those of you who don't know me, I have another screen that shows my video or my whiteboard. I'm going to go ahead and switch over to that. So I'll be back with you in just 1 second. All right. So today's plan is to introduce you to 2 more tests that are going to help us in this searching for convergence and divergence of series. And the 2 I'm going to show you today are actually very, very strong, really strong tests. They're really, really useful. And in fact, they are my go-tos. If I'm going to test series, I use one of these tests like 90+% of the time. The only time I don't use them is when they're going to fail, when they're not going to work, which does happen from time to time, and we'll talk about that. But anyway, let's just go ahead and build these things. So the first one is what we call the ratio test. And what's beautiful here in kind of classic mathematician form, we name everything exactly what they are. And so this is a test that uses ratios, aka fractions. All right. So what we're going to do when we do the ratio test is actually look at a fraction, and this fraction is going to tell us a lot about the series. So we're just going to go with our generic series here. I'm going to go ahead and say that it starts at 1, but it absolutely doesn't matter. We've got to do this eventually. And what we're going to do is we're actually going to look at the limit as n goes to infinity of the absolute values. So we're going to take absolute value of a ratio of terms. And what we're going to do is we're going to look at successive terms, so two terms in a row, and look at their ratio. So we're going to look at the ratio of the n plus first term over the nth term. So that just means we're looking at the next one divided by the current one. All right. So we're going to look at this limit, and let's go ahead and just call it L for the sake of having some sort of a number for it. Okay, so we're going to take this limit. We're going to look at this guy L. So here's what the ratio test says. If L is less than 1, the series converges. Done. Okay, so if that number, whatever that limit we get, is less than 1, we know immediately that series converges. Similarly, if L is greater than 1, we know that the series diverges. So think about how awesome this test is. This is one that, you bigger than 1, converge, less than 1, or sorry, bigger than 1, diverge, less than 1, converge. Like we just know what's going to happen just by looking at that limit. But if you're really paying attention, you may notice that there's a value of L that we haven't taken care of. Obviously, it's going to be positive or non-negative because of the absolute value. But if one of the statements is less than L and the other one is greater than L, the obvious other question then is, well, what if, or greater than 1, less than 1? What if it's equal to 1? All right, so this is going to be our third condition. And if L is equal to 1, this is the only thing that sucks about the ratio test, is that if L equals 1, then the test is inconclusive. Meaning, we don't know. It could converge. It could diverge. And we don't know. Because some series that converge will have a value of 1 from this limit, and some series that diverge will have a value of 1. So if this limit equals 1, that's the only time that you have to go, well, all right, ratio test doesn't work. So it's not perfect, and that's why when I said I do one of these tests like 90-some% of the time, the other 10%, that's when this limit's going to not tell me. But for the most part, this is really nice because it will tell you what is going to happen with your series. So what I want to do is actually just start with an example. I want to show you an example of using the ratio test, and then we'll prove it. Then we'll actually see why it must be. And then we'll do a couple more examples just so you can kind of see and play around. So suppose that this is the series we're curious about. So we're going to look at 3 to the n over n cubed. And I want to know, does that converge or does that diverge? All right, now if you think about your other tests that you know, obviously we could use the test for divergence real quick to take a limit as we go to infinity and see what happens. But if that is inconclusive, if that doesn't tell us anything, clearly we can't use the alternating series test because it doesn't alternate sign. We could try a comparison test, either limit or direct, right? But let's apply the ratio test to this. So here's what we're going to do. We're going to look at the limit as n goes to infinity of the n plus first term, which is going to be 3 to the n plus 1 over n plus 1 cubed. And then we need to divide by the nth term. So 3 to the n over n cubed. I'm not putting absolute values on there just because of the fact that it's always positive. So what we need to do is evaluate this limit. So I see Susanna just put in the chat that she thinks it diverges. Well, let's see. Let's do this limit. So since I'm dividing by a fraction, we'll invert and multiply. So this is going to be the limit as n goes to infinity of 3 to the n plus 1 over n plus 1 cubed times n cubed over 3 to the n. So we're going to be able to simplify this a little bit. The 3's, the 3 to the n cancels with all but one of them on the top. So we've got the limit as n goes to infinity of 3n cubed over n plus 1 cubed. And hopefully you remember the fast ways of finding limits of rational expressions. You basically look at the highest power on top and bottom. Well, they're both going to be cubes, so we look at the coefficients on them both. Well, on the top, there's a 3. On the bottom, there's a 1. So this limit equals 3. So in the language of what I wrote here with our proof, L equals 3. All right, so we go, well, 3 is not less than 1, it is greater than 1. Therefore, the series diverges. All right, so we know for sure this guy diverges, and I'm going to put here by the ratio test, because that's the test that we just used to show it. Turns out this one, the test for divergence, would have shown it if you just go to this original term and figure out what its limit is as n goes to infinity. You'd have to use L'Hopital's rule. Remember L'Hopital's rule, right? So if you do L'Hopital's rule a couple of times, you'll eventually get something where the limit is infinity. It's not 0, so we know that it diverges. Okay, but the ratio test told us as well that this thing diverges. So this is the process. This is all you're going to do. You're just going to look at the next term and divide it by your original term and take a limit as you go to infinity. Be aware of the absolute values. Make sure you put those in if you need them. I just thought I didn't need them in this case. And it's really easy to get these two terms because the one that goes on the bottom is just going to be whatever your series was as written. And then on top, you just change all the n's to n plus 1. All right, so that's how this thing works. It's really not that bad. Where you're not going to like it is with the algebra, trying to simplify and then evaluate the limits. That's where it's going to get tricky, but that's nothing new. You guys have seen that. But the hard part of calculus is the algebra. All right, but let's prove this. I don't want to just take this on faith because we can actually show why it must be. And the proof is not very hard, actually. And it's going to bring us back to something that a kind of series that we know and hopefully love. All right, so here I go. The proof of the ratio test. All right, so let's think about looking at that ratio and thinking about the two separate cases. The one when it converges and the one when it diverges. All right, so let's look at case number 1, which is going to be where that limit is less than 1. And I want to show you that if that's less than 1, we get convergence. All right, so that means that this thing, a sub n plus 1 over a sub n, as we go towards infinity, it goes towards L. So if I just take any two terms, like any of them, I don't know that this ratio actually equals L, but it's going to get really close to L, right? Like really close to L, as close as we want to L. That's what it means for that limit to exist. And so what I'm going to say then is that there is some number R that this is going to be less than. That R is going to be very close to L, right? Really close to L. Is it bigger than L? Maybe. Is it smaller than L? Maybe. But regardless, it's really, really close. Now, the other thing I can tell you about R is that this R is also going to be less than 1. I'm going to at least pick it so that it's less than 1. It's either going to be less than L, which already means that it's less than 1. Or if it's bigger than L, there's still going to be space between L and 1. There's always space between L and 1. No matter how close L gets to 1, there's always space. And I'm going to find the R that is still within 1. That's still close enough to L. I just might have to go further down line. Okay, but I can promise you there is an R where this is the case. All right. And this is going to be true for all n. And I'm going to put here eventually. Meaning if I go far enough down this list, eventually every ratio is going to be less than R. It just will, because of the fact that this limit exists. Okay, so that means that the n plus first term, or at least the absolute value of it, is going to be less than R times the absolute value of a sub n. Just doing a little bit of algebra on that, right? Multiply by the denominator. Okay, now there's going to be a subsequent one that says the a sub n plus 2 term is going to be less than R times the a sub n plus 1 term. Well, if I just insert this bit right here, drop that down, that's going to be less than R squared times a sub n. And I'm just going to do one more because then I think we're starting to see the pattern. The n plus third term is less than R times the second term, n plus 2 term. Well, that was this. I multiply by another R, we get R cubed times a sub n. And I'm going to put dot, 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 because the same thing's going to happen. Keep going on. Okay, so so what? Like, yay, this is true. Well, let's take a look at these guys. Let's look at the series that's made up of these terms. So suppose I have R times a sub n plus R squared times a sub n plus R cubed times a sub n plus dot, dot, dot. I can factor out the a sub n business. And I get R plus R squared plus R cubed plus dot, dot, dot. And just notice what's in the parentheses here. That's an infinite series. What kind? What's the name for that kind of series? You know, the kind where you multiply by the same thing every time. Well, that was close, Susanna. Go with the other option. There you go. Not factorial. Not arithmetic, but geometric. This one's geometric. There we go. Good job, Susanna. All right, so this guy's geometric with r equals r. The little r equals big R, right? Every time we end up multiplying by r. So we know everything about the geometric series. We know when it converges, we know when it diverges, right? So this converges if r is less than 1. But we already know r is less than 1 because of how we constructed this. So r is less than 1, which means that it converges. So if I were to take all of these things and add them up, I'm going to get a convergent series. Okay. Well, we've pretty much proven the ratio test, or at least this part. What's the last link? What's the last link to jump from this thing converges to our original series convergence?
Do we set them equal?
We're actually not going to set them equal because they're not equal. But think about what you just said about setting them equal. You're trying to compare them, right? Compare those two.
Compare an inequality.
Yeah, we know that our series terms, A1, N1, N2, N3, those things are less than these series terms. So this is when I should actually pick on Alexi because she offered this up for, well, I think it was question number 2 on the quiz. We can use direct comparison test. The series that we're looking at has terms that are smaller than this convergence series, which means our series must also converge. So there you go. When L is less than 1, it must be that our series converges. And even better than that, and I don't think I put this word down in when I wrote down the ratio test, but this is even better convergence than just convergence. I know it converges absolutely. Because I'm looking at the absolute values of my term. This is the other reason ratio test is really nice, because it gives you absolute convergence. There's no question of, is it absolute or conditional? Nope. If the ratio test says it converges absolutely. All right, so there's your proof that the ratio test does show absolute convergence if L is greater or less than 1. All right, so what about case 2? What about L is greater than 1? How do we show that there's divergence? Well, you do exactly the same thing. You just make your R now bigger than 1. And we know that this absolute value is going to be greater than R. It changes all the inequalities. So we're still going to be comparing it to this series, but now this thing is going to be diverging because R is bigger than 1. And then again, by comparison test, we've got terms that are bigger than a divergent series, therefore it diverges. All right, so I'm not going to show you case number 2 because it's pretty much the same. But I do want to talk about what about when the limit equals 1? And really, I want to show you two series where the limit equaling 1, one of them diverges and the other one converges. All right. So let's look at our good friend 1 over n. You know what that does. Harmonic, it diverges. But let's actually do the ratio test on this. So we're going to do the limit as n goes to infinity of the n plus first term over the nth term. Again, I don't need the absolute values, but I'm just doing that to kind of remind you what we need to do here. So let's go ahead and flip those over. We got 1 over n plus 1 times n over 1. So again, this is a rational expression. And you take that limit and you end up getting 1. So here is a series that we get a limit of that equals 1, and it diverges. Not because of this one, but it diverges because we know it diverges. The harmonic diverges. All right, well, the other series that I'm going to show you looks a lot like this one. It's going to be 1 over n squared. Another series that we know everything about. So that one converges by the p series, or the integral test if you want. But it's p series. But check out what happens when we do its limit. Okay, so we're going to get 1 over n plus 1 squared divided by 1 over n squared. So that's the limit as n goes to infinity of n squared over n plus 1 squared if you flip and multiply. And again, you take the limit on this and you get 1. So this is why if you use the ratio test and you get 1, that it's inconclusive. Because sometimes they converge, sometimes they diverge, you never really know. So if you ever run into that, if you ever run into a limit equaling 1 from your power series, doing the ratio test, okay, pick something else. Pick some other test to try. All right, anyway, so there's your proof. There's how these things work. So let's do a couple more. Let's play a little bit more with these, try a couple more ratio tests, and then I'll show you the root test. So here's another one, another example. Let's try this guy. Let's look at 2 to the n over n plus 1 factorial. So factorials, when they're in series, really kind of limit a lot of the tests you can use because things like the integral test go away and all that. And so, but what's really nice with factorials is the ratio test really helps simplify them down. So let's try the ratio test on this guy. We'll take the limit as n goes to infinity. I'm not going to put absolute values because I don't need them. But there's my n plus first term. Notice that everywhere there was an n, I put in an n plus 1. And then my nth term, that's the one that we started with. So let's go ahead and flip it over. I'm going to simplify it at the same time. So I'm going to get 2 to the n plus 1 over n plus 2 factorial. Right? N plus 1 times n plus 1 factorial over 2 to the n. All right, now before I take my limit, I'm going to simplify this algebraically. Look at the 2's. 2 to the n plus 1. Those are going to cancel and leave me just a 2 on top. All right, now the factorials are also going to cancel. They're going to reduce down significantly. And because I haven't been in here with you guys working with you, I'm not sure how this is, but how's your factorial algebra? Are you getting good at canceling them? I hope. Because this is going to happen a lot with the ratio test. This actually reduces the whole n plus 1 factorial is going to cancel. with the factorial on the bottom and leave me just an n plus 2. So this is going to be the limit as n goes to infinity of 2 over n plus 2. So all kinds of stuff reduces here when we do the ratio test. All right, well, now we're good, right? We know how to do this limit. Limit as n goes to infinity on this is going to be what? What's that limit value?
Would it go to infinity?
I don't know. Does it go to infinity? What do the rest of you guys think? I shouldn't have said I don't know. I do know, but what do the rest of you guys? Does it go to infinity? Adam thinks it goes to 0. Lexi throws that in as well. It actually does go to 0 because we've got a finite number divided by a really large number. That's going to drop down to 0. All right, so this one, the limit of successive terms is 0. All right, so that now tells us everything we need to know. Does it converge or does it diverge? All right, good. It converges. Thanks, Alexi. So this guy actually converges, and I can even be a little bit stronger and say that it converges absolutely. But obviously it converges absolutely because the absolute value, these are already positive terms, but it's a convergent series. I want to point out real fast that these two forms, exponentials and factorials, you're going to really like these when it comes to the ratio test because they are going to simplify like mad. Exponents love to reduce themselves down because you're going to have one divided by another, and factorials do as well. All right, so when you have those forms, that's going to really push using the ratio test as well. You're like, okay, cool, stuff's going to cancel. All right, so there you go. There's one that converges. Absolutely. All right, so one more. Let's try this guy. Let's look at the series of n factorial over n to the n. So same question. Does this thing converge or does it diverge? Well, let's use the ratio test. So we'll do the limit as n goes to infinity of n plus 1 factorial over n plus 1 to the n plus 1 divided by n factorial over n to the n. So we're going to invert that, multiply, so we get n plus 1 factorial over n plus 1 to the n plus 1 times n to the n over n factorial. And now we get to evaluate this limit. All right, well, let's start with simplifying those factorials. The n factorial on the bottom is going to cancel with the everything but the n plus 1 on top. We're going to get just n plus 1. And then if you look at the pieces with the exponents, I'm just going to warn you really fast. We cannot simplify those. We can't simplify them because they have different bases. Unlike over here, they were both base 2, so we could just slash stuff off. Here, we've got a base n and a base n plus 1, so we can't actually do anything with that. So here's where we are at this point. Once we reduce that factorial, we've got n plus 1 times n to the n over n plus 1 to the n plus 1. But before you freak out and go, well, we're hosed, we're not actually. We're still good here. Because this n plus 1 that stayed from the factorial actually is going to cancel with one of them on the bottom. So I'll just erase that plus 1. So now we're at the limit as n goes to infinity of n to the n divided by n plus 1 to the n. So we're getting there. We're getting much better. All right, well, now since those are both to the n power, I can combine it into 1. So I get n over n plus 1 to the n. So at least compared to where we started with this ratio, it's a much nicer form. But we still need to take its limit. So at this point, you probably are just going to plug in n equals infinity. It's always a good idea. But notice what happens. The inside is going to be 1. That limit is 1. And then, of course, the exponent is infinity. So this is the form 1 to the infinity. And before you go, okay, that's equal to 1, not necessarily. This is an indeterminate form. So what we're going to have to do is L'Hopital's rule. So I don't know how long it's been since you've actually played with L'Hopital's rule. You probably had a few of them pop up, like in the test for divergence section here. But L'Hopital's rule is going to be your friend with the ratio test. You're going to need it sometimes. So this is one of those where we actually have to take a log. So let me just remind you how this works. So if we're looking at, say, y equals n over n plus 1 to the n, we'll take a natural log. And what that does now is turn this into the form infinity. Remember, we're letting n go to infinity. Infinity times 0, because the natural log of 1 equals 0. That's still indeterminate form, but it's much closer to what we need for L'Hopital's rule. And the trick with this is to just divide one of them by the other. So n is the same as dividing by 1 over n. And now this is 0 over 0, which is the form that we can apply to, or we can apply L'Hopital's rule. All right, so if we do L'Hopital's rule on this, differentiating the natural log. So we're going to do big old L'Hopital rule equals the derivative of the natural log. Well, the bottom, we get just the stuff inside, so n over n plus 1. And then on the top, we need the derivative of what's inside. Well, that's quotient rule. So the derivative of n plus 1 minus n over n plus 1 squared. So that's the derivative of what's on top. And then the derivative of what's on bottom is just minus 1 over n squared. And I know that looks really horrible and nasty. It's not as bad as you might imagine. We're going to get 1 over n plus 1 squared times n plus 1 over n. And that whole thing is divided by minus 1 over n squared. So if we flip stuff around, we get minus n over n plus 1 once everything gets simplified. On that one, we can do the limit. Limit as n goes to infinity is minus 1. All right, I know what you're thinking. Oh my God. L'Hopital's rule, algebra, he's flying through this. I have no idea what's going on. Okay, I know I'm going through this kind of quickly because it's stuff you've seen before. You can also go and watch this video and see the steps again. But we now have our limit value. And before you jump to the, okay, that's less than 1, it converges, realize that this isn't actually the limit we're looking for. This is not the limit you're looking for. This is the limit of the natural log of y, right? We took a natural log. So we know that the natural log goes to minus 1, which means y is going to go to e to the minus 1. So that's actually what our limit equals. The limit as n goes to infinity of this thing is 1 over e. And that's the number that we need to compare to 1. So the question is that bigger than 1 or smaller than 1? Well, if you use your calculator, probably what your first instinct is, you'll see that it's less than 1. E is like 2.71828, right? So it's around 3 roughly. So this is around, it's between a quarter and a third. So it's right around 0.3-ish. Or no, it's a little bit bigger than a third. So it's probably about 0.4. But regardless, it is less than 1. And because that's less than 1, I know that this thing converges absolutely. All right. So some takeaways from this one. First of all, this is about as rough as they're going to get when you use the ratio test. There are some forms that are even worse, but then you usually use another test. So this is about as bad as they get. Review L'Hopital's rule. I can't stress that enough. Make sure you got L'Hopital's rule down because we're going to be doing lots of limits as you go to infinity here. All right. And then the one other thing I want to mention about this is that, yeah, it's going to take steps, but take your time, do your steps, keep track of where you are. These are not the kind of things you want to rush through. Make sure you keep track of where you are and you should be good. All right. Well, if you look at this original series and you look at the pieces of it, the piece that was really the problem, the piece that made this limit taking horrible was this guy, the n to the n. The n factorial was beautiful. I mean, that canceled away right away. It was the rest of it, that n to the n business, that made it a little bit tough. So that form is a form you kind of want to watch out for when you're doing ratio tests. And maybe if you have n to the n, you don't want to do ratio tests. Factorials and exponents with constant bases, you love with the ratio test. But when it's something like n to the n, reconsider. Okay, but then you go to the place in your mind where you're like, well, yeah, Bruce, okay, great. You tell me I want to watch out for those things and not do it. I need to have another test. I need another test to be able to tell whether it converges or diverges. Yeah, well, this is your next test. This is going to be the root test. All right, so let me show you the root test. The root test is actually very similar to the ratio test, where we're going to take a limit of terms here, basically, and that limit value is going to tell us convergence or divergence. And for the root test, what we're going to do when we take our limit, we're going to go limit as n goes to infinity, but we're going to look at the nth root of a sub n. Hey, look at that. A root test has something to do with a root. All right, now, technically, we need absolute values there. Sorry about this, my phone cord is not sure. Okay, so technically we need absolute values there, and you can probably see why. This n, it changes every time, right? So if we were starting at n equal 1, this would be the first root, which is not a radical, and then it'd be a square root, and then the cube root, and then the fourth root, and the fifth root, sixth root, seventh root, so on. And for even indices, square root, fourth root, sixth root, and so on, having negatives inside the radical is a problem. So we're going to throw absolute values on this in here. Okay, so we're going to take this limit, and again, we'll go ahead and call it L. All right, so now L tells us everything. So if L is less than 1, and it's going to be positive again because of the absolute value, but if L is less than 1, then the series converges absolutely. If L is greater than 1, the series diverges. And if L equals 1, the test tells you nothing. So if you just had a little deja vu, you should. This is identical to what we saw with the ratio test, right? The exact same results will lead to the exact same things with the root test and the ratio test. So that's awesome. That part's great. You don't have to worry about learning anything new. It's just we're evaluating a different limit now. We're looking at the nth root of our term as opposed to the limit of successive terms. All right, so this is the root test. And the root test is perfect for those n to the n kind of things. Let me show you. Let's do an example here real quick. All right, so let's look at the sum of minus 1 to the n over n to the n. So this was an alternating series. So that's cool. But if we wanted to look at like absolute convergence, we're going to be left with a 1 over n to the n, and Lord knows what happens with that. And I would rather not do the ratio test on this because I don't want to have n plus 1 to the n plus 1s and n to the n's. And oh, no, I don't want that. So instead, let's do the root test. So we're going to take the limit as n goes to infinity of the nth root of the absolute value of minus 1 to the n over n to the n. And I'm definitely putting my absolute values in there now, since these things are sometimes negative. All right, well, let's simplify this algebraically. So in the radicals, that's just going to be 1 over n to the n, because the absolute values cancel that minus. And the nth root, I want to remind you that another way of looking at radicals is to think of them as exponential powers. So the nth root is the same as 1 over n. All right, well, if I distribute this exponent through, this becomes the limit as n goes to infinity of 1 over n. Because 1 to any power is 1. And with the other one, I multiply exponents together, and n times 1 over n is 1. So I get n to the first. All right, so limit as n goes to infinity on this is 0, which means I know now that this thing converges. Absolutely. And it was fast. Fast and easy. So here's the deal. The reason that the root test was nice here is that the nth root canceled out that nth power. So this is why when you have something raised to the n, using the root test can actually be pretty quick. So let me show you another one. We'll do a couple more here. Let's look at this series where what we're going to add up is minus 2n over 3n plus 1. And we're going to raise that to the 2n power. So this is one where if you tried to use the ratio test, oh good Lord, it would be horrific. It would be absolutely horrific. But the root test is going to be actually really fast and easy. So we're going to take the limit as n goes to infinity of the nth root of the absolute values of minus 2n over 3n plus 1 to the 2n. All right, so again, I'm going to put absolute values on there just to make sure since there's a negative. But now let's simplify that algebraically. Absolute values take care of the minus sign. So we got 2n over 3n plus 1 to the 2n. And that's going to be all raised to the 1 over n. All right, so now the 1 over n times 2n just becomes a 2. So I get the limit as n goes to infinity of 2n over 3n plus 1 squared. So to evaluate this limit, I just have to take the limit of the inside and then square it, because that's what the rules of limits let me do. This fraction on the inside becomes just 2/3. And when squared, that becomes 4/9. So this limit is 4/9. All right, well, 4/9 is less than 1. So this is another one I know converges absolutely. So this is the kind of thing that you're going to recognize that you got that's going to push you towards the root test. Anytime you've got an exponent with an n, because that's going to get canceled when you take the nth root. All right, so there's your last test, the root test. Now I'm not going to prove it. I'll let you look at the book because we're kind of running out of time here. But I'll let you look at the book and decide, if you want to believe that proof or not. I'll also push you towards Larry. Larry will answer that for you if you have questions, or pop to my office hour if you guys want to come visit me. Come find me somewhere. But anyway, there's your root test. Now, before I give you kind of a wrap up of all the different tests and when to use them, I'm going to give you
Bruce's, here's how I decide what test to use and kind of the hierarchy. I want to just talk a couple more things. The root test compared to the ratio test, we already saw that like it's that same thing with the L's, and it's 1 greater than less than. And you notice that for both of them, if the limit equals 1, you don't know anything. And in that case, you have to try a different test. Don't go from the ratio test to the root test or from root to ratio, because they're one and the same. And here's what will happen. If you do a ratio test and you get a limit of 1, you try the root test, you're going to get a limit of 1, and vice versa. Okay. So if either one of these root or ratio tests ends up being inconclusive, don't go to the other one, because you're just going to be wasting your time, because you're going to end up with another inconclusive result. All right. Then you need to go somewhere else. Okay. So just realize that that's the case. And again, there are some forms that are really good for each one of these, and there are some forms that are really bad for each one of them. All right. In general, if you have a sub n is a rational function, which means it's a fraction, right? So we don't have powers of n or anything. It's just a fraction of polynomials. Don't use either of these. Because you're going to get a limit of 1 always with those. All right. So if it's a rational function, don't use the ratio or the root test. Factorials and exponentials and I mean like literally exponential functions, a to the n, where a is a constant. These guys love the ratio test. Because all kinds of stuff cancels out. It will be really easy to do. So that's the kind of form that's going to push you towards the ratio test. And in terms of the root test, stuff, sorry, I'm getting really math technical. I know it's been a while. So just stuff to the n really is going to suggest the root test. No matter what that stuff is, if you raise to the n or some multiple of n, that really is going to suggest trying the root test, because it will, the nth root is going to cancel that raised to the n. Okay, so that's just a little bit about what's going to push you towards ratio or root test and what to avoid. All right, so let me just give you some advice when it comes to trying to prove convergence and divergence with series, because I know now you have a bunch of tests, right? You probably have about like 8 or 9 of them. There's a ton. The question is what to use, when to use them all. All right, now here's what I do. The very first thing I do is I look at my nth term and I see if I can do a real quick test for divergence. Right? Sometimes it's pretty clear what the limit is. Sometimes it's a little bit harder to do. Like think about this one I have over here in the orange. It's pretty easy to see that those terms go to 0. 1 over n to the n. Right? Those terms are going to go to 0. So test for divergence doesn't tell me anything. This one, it's not as easy to see what the limit is as n goes to infinity. Right? It's a little bit more difficult to see. And so if I don't see it right away, I'll just step off. But I always look at that first, because sometimes it's pretty easy to see. And you can go, oh, those things don't go to 0 divergence. So that's usually just a real quick mental check. But I don't spend a lot of time on it. It's one of those, if I see it and I see it doesn't go to 0, I immediately write diverge. If I don't see it, or I see that it goes to 0, I immediately move to another folder. Okay, after I do that, I tend to go to the ratio test. I go to the ratio test unless I see stuff to the end, then I'll go root test. Or if I see that it's already a rational function, or if it's a form I already know. And what I mean by that are things like geometric and p-series. Because those are really easy, right? Like p-series is incredibly easy. And geometric is pretty quick. So if I see that it's going to be a p-series or like a p-series, I go that direction. If I see it's geometric or think it's geometric, I go that direction. All right. And it's for the ones that are not easily recognizable forms that we really have to discuss this anyway. And I go to the ratio test. If that limit ends up equaling 1, then I reassess and I try something different. Alternating series test is really easy to tell when you can use it, but it's also only good for convergence, not absolute convergence. Like you won't know if it's absolute or conditional. So I tend not to use that one. I would rather know if it's absolutely convergent. It's a little bit stronger of a statement than just convergent, right? But alternating series, it's very clear usually when you want to do that. And then when it comes to comparison tests, kind of like I was talking about earlier, when we were looking at that one from the quiz, I very rarely use direct comparison test. Very rarely. Most of the time I do a limit comparison test because it's a little bit stronger. It's you don't have to worry so much about, well, is this thing actually bigger than the divergent series I'm testing against, or are those terms actually smaller than the convergent? That doesn't matter when it comes to comparison tests. So long story short, real quick test for divergence. See if it's a form I know. If it's not, I go to ratio test. If ratio test is inconclusive, then I backtrack. And if ratio test doesn't look like it's going to work, I use the root test. So that's why I say, 90+% of the time it's ratio and root. It's the small number where I know that they're not going to work, that I do something else. Or even if I don't know they're not going to work and I find they don't work, that they're inconclusive, then I go to something else. All right, so there are your different tests. I'm going to hop back to my computer real quick. Let me, I'll rejoin you here in just 1 second. All right, so there's a little bit about ratio and root. If you have any questions, obviously you can hunt down Larry and ask him, and I'm sure he'll be happy to help you out. As will I, actually, if you guys can find me. I know it's a little bit tougher when you're not actually on campus. So in terms of this series stuff, you're probably wondering, why the hell do we care about all this? Seems kind of like we're doing math for math's sake. I'm going to not play spoiler for Larry because I don't want to do this to him, but I am going to tell you that where you're going next is probably one of the coolest things that you're ever going to do in calculus. You're going to find out, there's a little bit of a spoiler, you're going to find out that functions that you know and love can actually be represented as polynomials. Like all of them can. Sine of x, there's a polynomial for it. E to the x, there's a polynomial for it. And you use series to do this. They're called power series. But that's why you're going to care about convergence and divergence, is because in order to turn functions into polynomials, which are way easier to deal with. I mean, think about it, calculus on polynomials, integrate, differentiate, please. Please. Well, in order to do that, in order for it to actually work, you're going to have to know when those series converge. So please take this seriously.
because you're going to need it for the rest of this course, but you're also going to see it next year. In fact, I'm teaching differential equations right now, which is the last class we offer. So for some of you, that will be in the spring of next year. When you get there, power series come back like in a big way. So just be aware that where you're going is a really, really important thing, and it requires being able to do this convergence and divergence stuff. So practice it now, so that later you're not thrown over it. So what do you mean by that, Adam? Social studies division? Oh, all right. Well, I guess it was either a really good joke or a really bad joke, because I completely didn't get it. But anyway, that's all good. All right, so with that, I'm gonna go ahead and call this a day, but I do want to mention one more thing. Larry asked me to let you guys know. He got an email from someone who's looking for a tutor for their 5th grader this summer. So if you're in the area, if you're a Tahoe person and you'd like to maybe earn a little money helping out a youngster with their math over the summer, I'm going to have you contact Larry because he's got the contact info. I don't have it handy with me right now, but there is a tutoring opportunity. Okay, so make sure you let him know. And then I'm also going to remind you that you guys don't have class on Monday. It is Memorial Day, so the college is closed, so classes are not happening. So don't bother coming in on Monday because you will not see Larry in this classroom. You also will not see me in this classroom. But your next class will be on Wednesday. All right, so with that, I really don't have anything else for you unless you guys have questions for me. But it was good seeing y'all again. Well, at least seeing your names again, hearing a couple of your voices again. But yeah, have an awesome weekend, and I will see you guys whenever I see you. Cheers.
Bruce, I have a question.
Sure, Lexi.
On the limit comparison test, do you have to compare it with something still like the direct one? You just have to do a little more work?
Yeah, so both direct and limit comparison tests, you're comparing against another series. So you do pick another series.
Okay.
And it needs to be a series that you know what happens with it, right? You need to be able to tell whether that one converges or diverges. But
Yeah.
either way, you're comparing it against it. So direct, you're just going term by term. Are they bigger or smaller?
Okay.
And then limit is just looking at the limit of the two generic terms, right? So AN and BN.
If it doesn't equal 0 and it says like that both converge or both diverge, do you base it off of the other one that you found?
Yes. Yeah. So let's say you're comparing these two and you get a limit of 1.
Yeah.
You go, all right, it's not 0, right? It's finite and positive. So I know then that they both do the same thing.
Of whatever.
That's really the way to think about it with limit comparison is you get that number. If it's greater than 0 and not infinite, they both do the same thing.
Okay, cool. Thank you.
Yeah, you're welcome. All right.